Good job, Zoom. All right. We'll start off today by looking at this one. So part A, we want to show the alternating series test to show that this series converges when x equals 3. Now, something that you should get in the habit of is making sure before you start, you have a plan for what you're going to do. Since I'm using the alternating series test, I need to show or at least determine if this is in fact an alternating series. Once I've established that the signs alternate, I want to show that the limit as n approaches infinity of a sub n, the nth term formula, -1 to the n x, I'm sorry, not x, it's going to be 3 to the 2n, right? Divided by 2n factorial, let's go to approach 0. And then I need to, in some fashion, determine whether or not the terms are decreasing. So, first things first, I noticed that the terms alternate signs. You could have looked at several terms, that would have been fine. The terms in question come from this series here, when 3 is to the 2n power. Now, to determine that that was 0 took some doing, because when I looked at it first, I was like, yo, infinity over infinity, so I should do some L'Hopital's rule action, right? Yeah, you had that thought too, didn't you? And then you're like, what's the derivative of 2n factorial? Which is the correct response. So instead, I thought about how 2n factorial dominates 3 to the 2n. Right, as n approaches infinity, 2n factorial will eventually outstrip the performance of 2n factorial. Okay, so that means that is true, which means I need to determine if this is the case. Okay, so the n plus 1th term is 3 to the 2n plus 2 power. We talked about that in class yesterday. Divided by 2n plus 2 factorial. A sub n is again 3 to the 2n divided by 2n factorial. Remember, we're looking at the absolute values here because we're talking about magnitudes. So few ways you could think about this. You could look at terms, okay? So you could look at how 3 to the 2n plus 2, sure, that's bigger than 3 to the 2n, but 2n plus 2 factorial is always bigger than 2. Always going to be the case. Something else you could have considered using some cross multiplication, 3 to the 2n plus 2 power times 2n factorial. That's going to be less than or equal to 3 to the 2n power times 2n plus 2 factorial. That's definitely the case. You could have also done some pretty fancy algebra here. What do I mean? Well, what happens if you divide both sides by 3 to the 2n power? What happens if you divide both sides by 3 to the 2n power? You can do that, right? 3 to the 2n is non-zero. Yes, we can do that, okay? So over here, 3 to the 2n, that becomes 1. Over here, what does 3 to the 2n plus 2 divided by 3 to the 2n turn into? Think about it. Use those exponent properties. It's going to be 3 to the 2 power, right? Because 3 to the 2n times 3 to the second is the same thing as 3 to the 2n plus 2 power. And the 3 to the 2n's, they make 1. So it's 3 to the second. And then I'm also going to divide by 2n factorial on both sides. So over here on the left, that makes 1. What about over here on the right? If you do 2n plus 2 factorial divided by 2n factorial, what do you have? That one you may not be quite as comfortable with. Let me write that out for you. So we have 2n plus 2 factorial, which remember is 2n plus 2 times 2n plus 1 times 2n, etc. Yes, that's what that one is. And we're dividing by 2n factorial, which is 2n times 2n minus 1 times 2n minus 2, etc. So what happens? Well, 2n and everything after 2n, that cancels to make 1. So let me ask you, is 3 squared 9 smaller than 2n plus 2 times 2n plus 1? It sure is. That's definitely the case because n has to be 0 or larger. So maybe not when n is 0, but not too long it takes for n to, or for values of n to exceed that. Okay. Part B, show that this series converges for all x values where x is a real number. Nope, not doing that. Too hard. Have to come back to it. Okay, part C. Consider the function f of x, where f prime of x is, hey, I remember that series. You guys remember that series? That's the series we've been talking about in part A. Okay. So first term, second term, third term, okay. So determine if f has a relative minimum, relative maximum, or neither at x equals 0. I know how to do that. I can determine if a function has a relative maximum or minimum by first determining where the function has a first derivative that equals 0 or does not exist, and changes sign. From negative to positive, right? Okay. Did you remember there is another way to do that? Which is that one. If the first derivative is 0 and the second derivative is positive, you would also have a relative minimum. That's called the second derivative test. Now, the reverse is true for the sign change and the sign of f double prime to be a relative maximum. So if we change sign from positive to negative, relative maximum, if the second derivative is negative relative maximum, yes, okay. Why do I bring these up? Because if you're trying to do the first one, you're going to have a hard time with that. The reason why you have a hard time with that one is because you need all the critical values. So think back to the first half of calculus. We get the critical values. After getting the critical values, we'd make our intervals. We check the signs on the intervals. We'd say positive, positive, negative, positive. Oh, sign change, relative extrema. The first derivative test is impossible here because we don't have all of the critical values. So we have to use the second derivative test, which means we're doing this. So the answer should go something like this. We'll have a relative minimum when this is true, a relative maximum when the other thing is true. I'd write that out. And then I'd show that f prime of 0 is 1. Why is it 1? Well, the first term is 1, and then 0 squared is 0. 0 to the 4th is 0. 0 to the 6th is 0. What would be after 0? X to the 6th divided by 6 factorial? Plus x to the 8th divided by 8 factorial. Okay, so that pattern persists. So we have 1 minus 0 minus 0. So not 0. Since it's not 0, the value of f, we have neither a relative minimum nor relative maximum. Okay. Okay. Let's go back to part B now. Part B we've actually done already. We did part B pretty much when we did part A. The only difference is the series we're looking at has x in place of 3. Everything else is the same. Alternate signs, right? Need proof for alternating signs? Look at the series in part C. It's spelled out there for you. This one is a little bit trickier to think about. It's still going to approach 0, but we need to be a little bit careful. X to the 2n divided by 2n factorial. So you're going to look at that and you're like, but it's got an x in it this time. It doesn't matter what x is doing. X could be 10,000. 10,000 to the 2n power is still, as n approaches infinity, getting dominated completely by 2n factorial. It doesn't matter what the value of x is. That's still 0. And then for the third thing, pretty much what I did here, but replace the x's, or replace the 3's with x's. So we end up with x squared is less than or equal to 2n plus 2 times the quantity of 2n plus 1. So as n approaches infinity, this stays x squared. This, however, approaches infinity, and I'm pretty sure x squared is smaller than infinity. Yep, it is. I just checked. Checked my math. All right. So I'm done going over that. I'm going to pause the recording here, see what questions we may have. All right, then. So that's f double prime of x. You could do a couple more things here. The first one is simplify, and notice how 10 divided by 10 factorial, the 10s would cancel, and you'd have 9 factorial. You'd have 8 divided by 8 factorial, the 8s would cancel to 1, and you'd have 7 factorial in the denominator. That's pretty nifty. Okay. So this right here is taking the derivative of this, right? Subtract 1, 2n minus 1, multiply by the old exponent, 2n. 2n factorial is a constant. And the 2n and the 2n simplify into 2n minus 1 factorial. So I have negative 1 to the nth power times x to the 2n minus 1th power divided by 2n minus 1 factorial. Pretty nifty math, I think. And you'll notice that matches what we have up here. Does the series start at 1 or 0? I don't remember. The series starts at 0. So that would not work. The series would now have to start at 1, n equals 1, but that's not a big deal. Okay, pretty cool. Pretty cool. So what are we doing? Not that. This. We're talking about determining if an infinite series converges or diverges. I promised you 2 more tests today, 2 more tests on Monday, and then 3 definitions on Monday, and we are done with the first half, which is actually most of the days of the unit because I've spread it out in such a way. We have less than 10 total topics in this unit, which has felt like a beast. And 1 more unit. Wow, we're almost at the end of calculus. How sad. Just kidding, we're not at the end of calculus. We're almost at the end of calculus. We're doing together. So I was told we're up to infinite series test number 7. If that is not correct, well, that was what somebody told me. So I blame them. And the 7th infinite series test, again, is an arbitrary title. We're just titling them so we're staying organized, because remember, y'all did home fun last night where y'all made lists of y'all's series tests, so they're all in one spot, hopefully. And you took notes on them to make it useful, okay? So this is a comparison test, the direct comparison test, to be precise about it, because there are 2 comparison tests. By the way, this is my least preferred of the two comparison tests. I'll try to show you, or I'll tell you why at the end, but you may figure it out once you see the other one. But anyway, this is called a comparison test because we are comparing two things. The two things we are comparing are the given series. So whatever the series is that you start off with, so it's like, oh, determine if this series is convergent or divergent. And that would be the series that you're given. And you need to come up with a similar series. Now, when I say similar, what I mean is similar, super helpful. I don't just mean similar though. It should be similar and something that you know the convergence or divergence of. And when I say similar, what I mean is check these two out. 1 divided by 3 plus 2 to the nth power, I would compare to 1 divided by 2 to the nth power. That's what I'm talking about when I'm saying similar. So 1 divided by 2 to the nth power, while you're writing it down, I'm sure you're thinking about how that's a geometric series. R is 1/2, and the absolute value of 1/2 is less than 1. So that is a convergent geometric series. And I'll just say in general, when you're coming up with these similar series, we are typically using those named series like we talked about before. Like the P series, the geometric series, the harmonic series, although you can use the nth term test, you can use the integral test, you can use any test on any of your series you're comparing to, the one you come up with. But often you're going to have something that looks like a P series, looks like a geometric series, looks like a harmonic series, but it's not quite right. Not quite right. That was a good amount of time to get that written down. Yes? Yes? Okay. So what are we going to do with this? Well, we're going to compare the two series, and I'm going to arbitrarily declare one of the series A subscript n and the other series B subscript n, solely for the purposes of saying I have two different series here. So if I refer to both of them as A sub n, that could get confusing. So I'm not going to do that. Just going to say that we have two series, A sub n and B sub n. One of them is the original series. It doesn't matter which one. One of them is the new series, the one I came up with to compare to. That's B sub n. And we're going to do some informal math proofs. I'm going to draw you some sweet pictures. And by sweet pictures, you know what I mean. Barely helpful. Okay. So let's suppose that there are only two outcomes for A sub n. Actually, that's not true. There are only two outcomes for A sub n. One of those outcomes for A sub n is A sub n goes a little something like this. So we'll say that A sub n is converging. I know that things that decrease are not necessarily converging, but just pretend that that's good enough, okay? So we'll say that that's good enough to say that A sub n is converging. All right. Let's also suppose, we don't need to suppose, again, it's 100% true. There's only other one outcome. A sub n could be divergent. Those are the only two things that A sub n could be. A sub n could either converge, A sub n could diverge. A sub n could be bounded, A sub n could be unbounded. Those are the only possibilities in this particular universe. Okay. Now, here's what we're going to say. Relative to B sub n, these are the things that could be true. Either A sub n is less than B sub n, or A sub n is greater than B sub n. That could be true over here too. right? If you're comparing two things, we're going to say that one's bigger than the other. That's what we're saying here. That's what the green, I'm sorry, not the green, the red and the blue are. We're just saying one is bigger than the other. We're going to say that they will never be equal, which I think is reasonable, right? If I have one series, I'm not going to come up with the exact same series to compare it to. So one of them has to be bigger. They can't be equal, okay? So you still with me? All right, just looking at graphs. Supposing that A sub n is less than B sub n, A sub n looks like this. What does B sub n look like? I don't know. Could it look like that? Sure, it could look like that, but that's not the only possible outcome. It's also the case that B sub n could go like that. It's true if A sub n is less than B sub n, B sub n could be pretty similar to A sub n and converge, right? That's possible. Or it could be pretty different from A sub n and it could diverge, okay? How about over here, if A sub n is less than B sub n? Does the same thing happen? Are there two outcomes? Let's find out. So A sub n is doing this. A sub n is less than B sub n, so B sub n has to start out higher than A sub n, right? Okay. Can B sub n go like that? No, that's not allowed. How come? Because here they are equal, and here B sub n is less than A sub n. That's not possible. Okay, I can't do that. That's a no. Get out of here. It's got to be something like this, right? Has to be something like that. So if, okay, got it? Got it. All right. So let's go back to the first one. A sub n is bigger than B sub n. So what does that mean? That means that if A sub n starts here, B sub n has to start somewhere less than that, right? Yes. Okay. And what has to happen? Well, if A sub n is going down, B sub n's got to do that too, doesn't it? Right? It can't cross A sub n. That doesn't make sense, because if it crosses, they're equal, and they can't be equal because then they'd be the same series. And what are we doing here if we're comparing the same series to itself? Over here, though, B sub n is, oh, that's like the same. Pretend that's not the same. There we go. Okay. Could do that, or could do something like that, right? Those are the possibilities here. So what I'm saying is there is some complexity here. Here's the complexity that we're going to take out. If the larger series converges, the smaller series must converge. That is in the first picture. That is what has to be true. This is a series that converges. If that series is larger, the smaller series has to converge. If the reverse is true, anything's on the table. For the second picture, if the larger series, if the smaller series diverges, the larger series must diverge. Like, that's what has to happen, because remember, these cannot cross each other. This is the essence of the direct comparison test. The direct comparison test is taking one series that we're given, comparing it to another series that we need to come up with that's going to be similar, and not just similar, it's going to be one of the ones that we've studied, because it'll be quick to determine the convergence or divergence of, and then we'll compare them directly. So let's do that. We're going to come up on another quick break here. And what we're going to do is, on our break, besides taking a break, you're also going to think about what series should this series, the given series, be compared to. So if we compare that series to another series, what ought we to write for that other series? This is a good place to pause the recording. Continuing here, the most popular in-person answer was some version of that. Okay. So what do we know about that series right there? We know that that series is a convergent geometric series, but there's something really important we need to think about. So how do I know it's a convergent geometric series? Well, it's a geometric series because I'm multiplying by 1/3 each time. And I know it's convergent because the absolute value of 1/3 is less than 1. So here is, I don't know if you overheard me talking to one of the students, but I was saying I'm reluctant to declare this one to be B sub n and that one to be A sub n. I find that confusing. Let me show you why. If this series converges, we would like to use that fact to show that this original series converges, right? That's what we want to do, okay? We're comparing them together. This converges, that converges. So in order for this series to converge, I need the green series to be larger. Right? If the green series is smaller and the smaller series converges, that's the blue version of the first picture. The smaller series converges. The larger series could converge or diverge. We don't know. We need, if the series we come up with converges, we need the series that we're given to be smaller. So let me draw that for you again right here. So maybe you'll have some idea of what I'm referring to. So axes, I know that this series is doing some version of that. I need my original series to converge, which means my original series has to be smaller. That's the direct comparison part. I need to look at this series right here and in some fashion determine that that series is smaller. Now there's a few ways you could do this. You could do this by literally calculating values by hand, which I know you can do. It's like n equals 1, that's 1/5. N equals 1, that's 1/3. 1/3 is bigger than 1/5. N equals 2, 1/11. N equals 2, 1/9. 1/9 is bigger than 1/11. So you could do it that way. You could do it on your calculation device. Pull up the table, look at the table. You could try to do it on your calculation device with a graph. Pull up the graph. You could use a more descriptive argument and say that 2 plus 3n is always larger than 3, sorry, not 3n, 3 to the power of n, is always larger than 3 to the power of n when I compare them. Therefore, as they're in the denominator, 2 plus 3 to the power of n, the denominator here is larger than here, 3 to the power of n, that's smaller. So you want to do something like that. And once you've done something like that, you should probably communicate you've done something like that. So I've left a lot of that writing out. I did it out loud. But nonetheless, if we've done the comparison correctly, this will work out. Now, a real quick note before we go on to the next direct comparison example. I'd just like to say that if your first comparison doesn't work, it's perfectly fine to try another comparison to see if you can get it to work. It's also perfectly fine to say, you know what, maybe a comparison test doesn't work. I should try a different test, of which I will have 9 to choose from. So let's look at this next one. And for this next one, I want you to take a few moments while you're copying it down and as much of the last thing that you need to get copied down. I could scroll up a little bit, sorry about that. I was definitely talking and thinking faster than maybe you could write. Think about what series you might want to compare this one to. So what should we compare that to? We're not going to take a whole lot of time here to check that out. But just think about it as long as you're writing. Looks like about 10 more seconds. You don't have to write down an answer. I just want you to think about it. What would you compare it to? For me, I had a couple of ideas. Okay. One of the series I came up with was this one. That seems to be pretty close, right? Pretty close. Okay. Let me ask you, what kind of series is that? You should be able to pretty quickly tell me that that is a harmonic series, so that diverges. Another one that I was thinking could work here is that one. What kind of series is that one? That should also be pretty quick for you by now. If it's not, you need to study up. That is a P series. P is 1/2. That will diverge as well. Regardless, I need to show in some fashion which one is it? Do I want my new series bigger than the original series? Or do I want my new series less than the original series? Think about that for a little while. Which one of these do I want to be true when I look at my term-by-term comparison, either on the calculator or by writing some terms out, regardless of which series I use? By the way, I'm going to use this one. So do I want the new series I came up with to be bigger than this series or smaller than this series? According to the comparison test, when I compare the terms to each other, if the larger series converges, that's not it, is it? No, I don't know if the larger series, this is the one. I need the smaller series to diverge. So what I need to have here is this. So if I can get or show that, then it's going to work out. So you could do some terms, right? N equals 1, you have 1/3 and 1/3. So that didn't work out so good. N equals 2, you have 1. Okay, that didn't work either. I'm just going to skip to 4. Sound good if I skip to 4? Okay, if I skip to 4, square root of 4 is 2. That's 1/4. This is 6. Ooh, 1/6 is smaller than 1/4. Okay, I'm going to skip. I don't want to do 5, 6, 7, or 8. I'm going to go right to 9. So that's 1/5. How about this one? 1/11. That's still smaller. Okay. Then I'd skip to 25, 1/7, 1/27. 1/27 is smaller. So see what I mean, where you could write out some terms? You could also look at that on a calculator. Again, look at a table. Regardless, it is fair to say that this is the case, right? That is the case. And since that is the case, this also diverges. So that's the gist of the direct comparison test. I have a series. I come up with a new series. The new series, I should be able to determine using the integral test or the nth term test or the P series or the geometric series test if it converges or diverges. Once I know that my series I'm comparing to converges or diverges, then I want to be thinking about these two statements. So if the series I come up with converges, I need that series to be larger. If the series I come up with diverges, I need that series to be smaller. If I don't, I have an inconclusive result, so I wasted my time. So in terms of the universalness of this particular test, I would say that it is not universal, although it's more useful than the other named ones. And that's because we got to be able to come up with a comparison. So if you can't come up with a comparison, something that you know converges or diverges, you're not really going to be able to get far with the direct comparison test. Which brings us to, and I'll come back to here so you can write that down if you need to. Our next series test, the 8th one, the limit comparison test. And the reason why we're doing these together is because they're both comparison tests, meaning I'm again going to have to come up with a series that I know the convergence or divergence of to compare. So that part is the same. This one has limitations. But honestly, I prefer this one to the other one. But there's issues. This one too is not universal because there are limitations for the comparison as well as additional limitations. So this is how you do a limit comparison. You write a limit statement. So you write a ratio of one series to the other series. So one of those series is the one that you started with. The other series is the series that you came up with for comparison. And this one is a little bit different from the other tests, but also the same. And we're not going to look at a proof for where this test comes from because that proof would take probably more memory than Zoom would save. But whatever our result is, what we're looking for is for the result to be finite and positive. And if the result is finite and positive, then similar to the direct comparison series test, we're going to be able to say for both series if they converge or if both series diverge. That's what we'll be able to do here. So whatever the result is, so long as the result is finite and positive, we can say the original series the original series takes on the same convergence or divergence behavior as my comparison series. Now this is why we can't just use the limit comparison every time instead of the direct comparison. If we don't get a finite and positive result from the limit comparison test is inconclusive. It's just like the nth term test when you get 0 out of it for a series. It's inconclusive. It could still converge or diverge. We have no stinking idea. None. So this is why it's like a double secret, not universal here. I mean, we can use this whenever we want on any series we want, but we have those limitations. We have those limitations of being comparable, and we have the additional limitation of being inconclusive. Okay. Let's look at this series first. Assuming, of course, A and B are non-zero. By the way, have you noticed how for just about every test we've studied, This has been the first thing we looked at. Now we didn't do it for the direct comparison. But integral test, check. P-series, check. How come? Because that is the harmonic series right there. A, B, and C are constants. We're going to say that A and B are both non-zero. We already know that this diverges, yes? Yes, harmonic series diverges. But for the sake of argument and example, we're going to compare this to the harmonic series, 1 over n, as n goes from 1 to infinity, which we know is divergent. So we already know the result here is that it's divergent. We're going to use that knowledge to check our work to say, okay, we did this right, or nope, we didn't do that right. So we're going to compare this to a divergent harmonic series. Very uncooperative bit of stuff. Okay. So how do we do that? We write a ratio. We take A divided by Bn plus C. A, B, and C are constants. A and B are both non-zero. And we divide that by 1 over n, which, using algebra, multiplied by the reciprocal of 1 over n, means we have n over 1, or a numerator that consists of A times n. Okay, so we get that. Do you know why we get that? Do you? I hope so. Because we can apply L'Hopital's rule, because we get infinity in the numerator and infinity in the denominator. Infinity in the numerator and infinity in the denominator. So I take the derivative. A, B, and C are constants. The derivative of an is a. The derivative of bn plus c is b plus 0. Okay, now provided a and b are positive, our result is finite and positive, which means both series diverge. Got a finite and positive result from the limit comparison. That means both series diverge. Maybe you have some understanding of why I like that one better than the direct comparison. I find that one, for me, a little bit easier to manage. So I don't have to go through the whole, oh, which one's bigger? I don't like doing that very much. It's tedious. Okay. 1.5 more examples. This will be another time where we're going to take a break here. So I'm going to give you 2 minutes to come up with a series for comparison. I'm going to resume recording. Not that I'll be recording for too much longer here. How's that one grab you? Are those similar? I would say so. Kind of my reasoning here is when I look at 3n squared minus 4n plus 5, and I think about dominance, because again, this is infinite, n is approaching infinity. Out of everything in the denominator, what's the most important thing? N squared. N squared is what drives the behavior here. So I could compare this to n squared. Which, last time I checked, is a convergent p-series? Sound about right? Convergent p-series. Okay. So that's good. This is what we're looking at. Why, oh why does 1 divided by 3n squared minus 4n plus 5 divided by 1 divided by n squared, that limit as n approaches infinity of that function, why does that equal 2/6? Do you know why that equals 2/6? You should think about the algebra here. Why does that equal 2/6? Well, I'm pretty sure because I can write it using my division algorithm as n squared divided by 3n squared minus 4n plus 5, which is 0 divided by 0. So I can apply L'Hopital's rule not once, because that's 2n divided by 6n minus 4, but twice, which gives me 2 divided by 6. And the limit as n approaches infinity of 2 divided by 6 is 2 divided by 6, which is 1/3, yes? Result is 1/3. So as 1/3 is finite and positive, what are both series? Both series are convergent. They are convergent. Okay, here is the last one for today. I'll let you start thinking about that while you're finishing up writing about that last one. And we are not going to do the complete limit comparison test here. All I'd like you to come up with is what you think this compares to. So finish writing down what you need to for that second example. And this third example, all I want you to do is just think about what you should compare it to. What seems like a good comparison? How does that one sound? Hopefully good. Hopefully good.